Analyze the thermodynamic properties given. We are given that the standard Gibbs free energy change of the reaction at room temperature is delta G degrees 298 is equal to minus 33 kilojoules per mole of reaction. A negative Gibbs free energy value, delta G degrees less than 0, indicates that the synthesis of ammonia is thermodynamically favorable, spontaneous, at 298 Kelvin. Determine the equilibrium state of the reaction. Standard Gibbs free energy is related to the equilibrium constant, K, by the expression delta G degrees equals RT ln K. Because delta G degrees is negative, the equilibrium constant must be greater than 1, K greater than 1. This indicates that at equilibrium, the system is highly favored to exist as products, in H3, rather than reactants. Address the conflict between thermodynamics and observation. Despite the reaction being thermodynamically favored to produce ammonia, no formation of NH3 is observed when the reactant gases are mixed at room temperature. This indicates that the reaction is under kinetic control, meaning that while the final product state is highly stable, the physical rate of the chemical reaction is incredibly slow. Identify the molecular cause of the kinetic barrier. In order for a chemical reaction to occur, colliding reactant molecules must possess a minimum amount of kinetic energy to overcome the activation energy barrier, EA. Nitrogen gas, N2, is composed of nitrogen atoms held together by an exceptionally strong triple covalent bond, NiCoVan. Breaking or weakening this triple bond to initiate the reaction requires a massive input of energy, creating an extremely high activation energy barrier. Conclude the temperature effect on the rate. At a room temperature of 298 Kelvin, the average kinetic energy of the molecules is relatively low. Only an infinitesimally small fraction of the N2 and H2 collisions possess enough energy to clear this high activation energy barrier. As a result, the forward reaction is extremely slow and no product is observed, identifying option B as the correct explanation. The correct answer is option B. A high activation energy makes the forward reaction extremely slow at 298 Kelvin.